I'm happy to be here today, and I'd like to talk to you about some of our new research about architecture learning, which is resource aware. And I'll talk about the algorithm, I'll talk about some results, and finally also about the open source framework we have that each and every one of you can use on your data, on your task, on your model with minimal overhead. So let's start about the basic question of where do neural networks come from. So they come from this complex interaction between a human brain of a researcher or engineer with an accelerator, a GPU, that with many rounds of interaction and back and forth and intuition and trial and error comes up with some architecture which is good for some time. But then some time passes, and then we want to get even better performance, and other researchers around the world are fighting and experimenting and collaborating in order to get a better architecture with a lot of trial and error and intuition again. And yet another year passes or some more time, and we want to repeat this process. And again, there is some advance in the field. This is the ResNet architecture. But what happens if we want to do a little bit to scale this up and do something a little bit more principled? And I'd like to argue that this process of this cool interaction between the human researcher's brain and the GPU is not scalable, because there's only a handful of researchers in this planet that ever managed to come up with a really new architecture. It's not optimal, and even they didn't actually do that many times consistently. It's not optimal because even if they come up with these cool new architectures, they're not necessarily all the way 100% tuned. It's often possible to do better. And more importantly even, it's not customized to your data and your tasks, because usually most of these architectures are constructed having CIFAR or ImageNet in mind, whereas most of us, I would guess, actually do not care that much specifically about these data sets in production systems. And also they don't take into account your resource constraints, the throughput, the latency requirements, the model size requirements of your task. So there is like a great amount of literature and work about neural architecture search that tries to automate the process of finding new and better good architectures. In a nutshell, the way it works is that they define an architecture space where there is some topology, and each element can be chosen like a high-level topology, and each element can be chosen from a set of operations, some connected this way or that way. And with a lot of interaction between a controller, that could be an RNN or evolution, and again, a lot of compute, we get these new architectures that are very powerful often and performs very well. However, the cost is really skyrocketing. The first rounds of these approaches cost 22,000 GPU days, which is unimaginable for basically anyone. Even after the advance and cutting down this cost by orders of magnitude, you still need thousands of runs on a toy proxy data set in order to have a decent performance, which is also that infeasible, I would guess, for most of us. So what we want to propose is something different, something that we think of as architecture learning and not architecture search. And we'd like it to be efficient, to be scalable, and that would work for everyone. What do I mean by that? Is that it should be efficient and trade off in an interesting and good way, hopefully optimal way, the resource constraints that you actually care about and the performance. It has to be scalable in the sense that it only needs to allow you to use a handful of runs. You don't need to have an extra data center only for your architecture learning. And it has to be really custom for you. It has to train on your data, on your model, hopefully on your code, up to some fine print. And the idea is pretty simple. And the high-level idea is to have a continuous relaxation of the combinatorial problem of that is underlying the architecture learning. I'll explain in a minute. And the actual tool that we use is a sparsifying regularization term. And also I'll get into that. So in order to zoom in on what we are actually doing and what we are not doing, I'd like us to stare at this wonderful table of the description of Inception V2. Some of you know it already. And I'd like to first start with what we are not going to learn directly. And I think of it as the topology, which means the connectivity between different operations and the exact type of operation, meaning whether it's a convolution, what size of convolution, or an average pool, and so on and so forth. What we will focus on, which is still a very big space and I would think interesting, is the number of filters or number of neurons within each of these elements. The number of neurons might look a little bit limiting, but in fact, it also can affect the topology. This is a zoom in on Inception model. And if you think about it a little bit, you can shrink or expand different sizes of different elements. But actually, 0 is also a number. And you can learn that the number of filters should be 0, meaning that some branch could be thrown away. And this actually happens. In almost all architectures, modern architectures that I know of, there is always a possibility to throw away some parts of the networks, either because of residual connections that you can use the skip to actually not have some block, or more like an Inception style where you have a concat, and again, you don't necessarily have to have all the elements actually appearing there. So I was telling you about the main tool that we're using, which is a sparsifying regularization function. Let me go into a little bit of details because I want you to have a good feeling on what's happening. So 1 minute background about sparsifying functions. When I mean sparsifying, usually we mean something that has a few or controlled number of non-zero elements. This is like a toy example when your dimension is 2. So you want to you're interested about the corners of the polytope. And the classical way to relax this this constraint or this approach or this quantity is to use the L1 regularization term. So the L1 regularization term is very powerful in many settings. However, what it produces is exactly sparsity that looks like the upper vector there, where there are all kinds of holes, kind of zeros, in the matrix, in the weight vector that you're interested in, which is not very useful in the context of deep networks because most hardwares in most settings will not be able to take this sparsity pattern into account and make the network faster. So what we're more interested in grouping weights together. So fortunately, there is the group LASSO. Some of you are probably familiar with it, type of work that takes the norm, not the L2 norm, not the L2 norm squared of a set of elements. And this actually behaves very much like the L1 in the sense that if the L norm of some group is 0, so basically you don't need it anymore. It means that all the elements are 0. And in the context of weight matrices in deep networks, if you consider all the weights associated with one filter, this slice of the weight tensor, so it's exactly the type of weights that we will be taking together, grouping together. And if they're all 0, we basically do not need this filter anymore. So now that we have a little bit of a background about sparsifying regularizer, I can tell you the high level of the algorithm. So the algorithm will consist of 2 stages. The first stage, we think about it as a structure learning phase, where you train your network and the only difference is that you add a regularization penalty, this RW, that we'll talk about later, with some coefficient, lambda. And from this process, you'll train it, it will converge, and what you'll actually extract from it mainly is a structure, a new structure for your network. In the second stage, you will either fine-tune or retrain your network with the new found structure the same way you used to be doing that before. And as an extra step that can happen actually either before step 1 or after step 2, you can try to iterate on this process, expand your structure uniformly or however you want to, and shrink it back again. And I like to think about it as moving computational power that was wasted in some part of the network towards places where the network was more hungry for computation. So that's the uniform expansion. So this is the high-level idea of the algorithm, and I'd like to dig in now more with the details. So let's consider as a first example this simple CIFARNet from maybe 5 years ago or more that has only 4 interesting layers, 2 convolution and 2 fully connected layers with some average pool between them. And we'd like to learn its structure. Of course, we could do it brute force, basically, but we'd like to do it in a more interesting way. So we applied the regularization, we applied the first stage of learning a structure with different regularization strengths to get different networks. So you can see here that the numbers are smaller and somewhat different. These are made-up numbers, by the way. You can do that several times in order to get a performance accuracy trade-off. And we compare, so these are the blue lines generated with, blue dots generated with our approach. And we compare them to what one would do without any prior information. And the common approach is to simply use, sometimes I think about it as an axe method, and simply cut away uniformly filters from everywhere in the network, simply multiplying it by 0.8, and then you have a smaller, faster network that usually it works okay or pretty well, but we can do better. So if you look at the y-axis, it's the accuracy of the model, and the x-axis is the fraction of the original size of the model. I'm intentionally not telling you what are the exact units, but I'll get to that soon. So it looks like, okay, maybe we're improving a little bit if we focus on the y-axis of accuracy, but if we zoom in and try to think of what's actually happening there, and we fix accuracy and we see how smaller of a network we can get with this simple procedure, we see that we get between 20 and 50% speed up for the same accuracy. Of course, this is a toy example, and it has the characteristic that it's from before batch norm existed. So I think, as far as I know, all or most modern architectures will have batch norm. Batch norm is wonderful, but it has the interesting property that it creates that the weight matrix is now scale invariant. So basically, if you take the weight matrix and divide it by 2, or divide all the filters associated, all the weights associated with one filter by 2 or 7 or 79, you get the exact same output, not approximately, the exact same output. So basically, you cannot regularize using group LASSO a weight matrix in the presence of batch norm, because it will lead to eventually numerical instability and collapse of your network. Fortunately, whatever batch norm takes away from us, it also gives us back. A common way to think of batch norm is actually with a gamma parameter, sometimes called a scale parameter, that after normalization, you can rescale the activations by some learned parameter, gamma. This gamma is miraculously exactly the operational norm of this operation. And if we apply L1 on this gamma, we get back the property that we wanted, that we have a handle on a filter, and if we manage to push this handle to 0, the filter is essentially dead, and we don't need it anymore. So that's one of the key components that we'll be using in most of the networks. I said that, that our tool of choice in the high level is a weighted sparsifying regularization, and I'd like to zoom in on the weighted part. So activations are great. They're a proxy for the size of the network and time it will take to compute, but it's actually a nuisance parameter. Who knows actually how many activations your network have? I don't think that any of you actually know. What you do know is how much time it takes, how much resources it consumes, what is the size of the model in terms of number of parameters, what's the memory footprint. But you actually don't know and couldn't care less usually about the number of activations per se. Luckily, then most of these quantities that I mentioned, number of floating point operations and model size, can be thought of as some coefficient, some weighting function, times the element-wise regularization of, let's say, the batch norm gamma, the filter-specific regularization. So how does this coefficient look like, and what does it represent? So this coefficient will represent the marginal cost of one activation. So let's take the simpler case of a model size regularization. And let's look at this 5x5 convolution applied to a 7x7 image with depth 11. So what is the marginal cost of a specific filter? It's simply the number of weights associated with this one, which is exactly 5x5, because it's a 5x5 convolution, times the number of inputs, 11. So that's simple enough. So that would be the coefficient multiplying each and every element of this convolution for the regularization term. The flop coefficient is almost the same, but a little bit different. We have to also take into account not only the size of the weight matrix, but also the number of times it's applied. For this, you need to take a look, a sneak peek of the output of that convolution, and actually realize you're going to compute this 9 times for like 3 by 3. So all this is only to show you that this coefficient is very flexible and can point you to different interesting directions with a meaning that you actually care about. Could be model size or flops, and we'll get to other things later. So let's look at how this performs on more interesting problems. I am showing you here Inception V2 Based Networks working on ImageNet. And the baseline, again, is the uniform shrinkage of all layers, kind of performed as a baseline with a lack of a better option. The blue line is the flop regularization was generated using a flop regularization with different regularization strengths, as seen before. And the x-axis is the flops, and the y-axis is accuracy. And what we can see is, again, is a performance that is stronger than what you could achieve by brute force method, basically, of a uniform reduction. What we can see in the magenta and the turquoise, probably star, in the top right is what happens if you take one of the shrunken model and uniformly expand it exactly toward to tune it to have the exact same cost as the original model. And what we see is that this actually improves the model by, if I remember correctly, 0.6%. And you can repeat this process again. I didn't show it here for clarity reasons, but you can repeat this process again and get yet another improvement. And what I'd like to stress is that this is actually human-free almost. You only have to run it. You don't have to reason about what's going on and try to manually tune filters from one place to another. So that was also the ImageNet dataset, which everyone here probably knows of. But we wanted to do that in real production systems as well. And back then, we applied it to JFT. It's the internal Google image classification dataset. It's as you can imagine, it's somewhat larger. Back then, it contained 300 million images and 20,000 classes. As a side note, you can imagine that running architecture search that took 20,000 GPU days on CIFARNet would be somewhat infeasible even at Google with this size of data. And in this data set, you cannot really train thousands or not even hundreds of experiments. So you have to be mindful on how to use resources even in this setting. So we started with the ResNet 101, the yellow point there. And again, the baseline is what one would do without any prior knowledge, and reduce or increase the size of the architecture. And we see that there is this trade-off, and there's like under the hood some real constraints from the people paying for this model to be in production. So we cannot like increase it infinitely. And what we see is that using the flop regularization, we can dominate the curve, and for any resource constraint, we can perform in a better way. So this model, as far as I know, is the first model in Google and possibly elsewhere that was that the structure was automatically tuned and is serving in production. Each and every one of you, if you have Google Photos or if you use Google Images to search for stuff for your presentation. So it's actually under the hood to some degree using this algorithm as well. And also a lot of other things, of course. So just another point that I'd like to highlight regarding this approach is that kind of our thesis is that there's no one good model that fits each and every one of your problems of interest. So let's take the model from the ResNet-based model from the last slide and consider what happens if we shrink it uniformly and we get like 3 models with the same performance. It's mean average precision. So one of them can be reached by shrinking everything uniformly. It's the left-hand side. It's very block-wise. If you care about blocks, that's great. It's very square-like. But actually, if you care more about flops for as a proxy for inference time, or even electricity to some degree, you probably want to have the other model that is very non-human-like designed. It's based on the ResNet 101 model, but it has less layers, and the layers have all kinds of weird sizes. The widths of these colors represent the layer size. The details don't matter that much for now. The point is that for the same accuracy, it has 40% less flops. But maybe flops is not what you actually care about that much. For some reason, you care about the model size. Maybe you want to ship it to phones or to data centers or whatever, and you care about the number of parameters. So again, you can apply a different type of regularization and get a drastically different type of network on the bottom part here that has 43% less weights than the original one, and again, the same accuracy. And the point is, again, that there's no one, we don't believe that there is one structure that fits everyone's needs. And because the needs are changing between application to application and person to person, and also through time. Another application that is maybe less commonly thought of, because we are all kind of tuned to image classification, is OCR, which is actually a big problem and considered sometimes as a solved problem. It's solved only if you want to take a picture of one document and one page. But if you want to do OCR on the wild, on all possible scripts on the planet, so it's far from being a solved problem. So the Google OCR team, they deal with this type of problem. And as you can imagine, they have dozens or more, I'm not exactly sure about the number, of scripts they support. Arabic, Latin, Cyrillic, and many others that Japanese, Chinese, that I don't remember. And each script has very, very different characteristics. Obviously, they look differently. The complexity of the characters is different. Some of them are rounded, some of them are more square. The number of characters is different. The word length is different. The size of the data could be drastically different. All of these things are different. But classically, now we have only one basically architecture to rule them all. Why? Because no sane person would hand-tune an architecture for dozens of languages and maintain them over time. So there's only one architecture. So what we did it actually for many languages, but here I'm showing 2 of them. There's the Cyrillic alphabet and the Arabic alphabet. As you can see, they're somewhat different. So we applied the flop regularization with some coefficient and got models that are 50% faster, but have the same accuracy. So that's kind of, oh, that's great, but how can we get this free lunch on some production system? And the point is that the models that are learned are different. And the previous system was constrained to have one model that works for everyone. But we are no longer constrained with that if we have an automatic way to shrink the model for each language. So what I'm showing here is a plot where the x-axis is the relative size of a layer, a specific layer, when compressed within for the Arabic script, and the y-axis is when it's done for the Cyrillic script. So so each point is corresponds to a specific layer. So what we can see here is the diagonal is meaning that the layer is interesting enough in the same amount for both scripts. But actually, many elements are off diagonal. And the things above the diagonal are more useful in Cyrillic, and the things below the diagonal are more useful in Arabic. And it seems that once we have a way to figure it out, we can save on both ends of the spectrum in a pretty easy to use and automatic way. Hopefully, soon serving all of you when you use Google OCR. So, as I mentioned before, if we try to take a high-level look on the process of what we're trying to achieve. So we had in the beginning kind of, if you want to have like a faster network, you have the brute force approach. Mainly I was comparing of cutting layers with the width, with a width multiplier uniformly. And that's one approach. Another approach was to take the number of activations as a proxy, which could be we have a result that is already better than simply doing something uniformly. We then shown some results with the flop regularization, which is a much better proxy for latency, but it's not there yet. And the question is, if you think about latency, you automatically realize, and definitely in this audience, that this is device-specific. Latency does not exist in the abstract. It's latency on a device. So the question is, how can we tune device-specific latency using the same ideas? So what we use again, the first line of attack here is something that is sometimes referred to as a Roofline model. In the Roofline model, we know that we kind of assume that the inference time associated with one operation comes from two different sources. One of them is fetching the input tensors and the weight tensors and whatnot from memory, which is a memory cost, associated cost. And one of them comes from the compute, from actually computing the transformation at hand. So each device has some characteristic, which is the peak compute and the memory bandwidth, which are, again, not perfect measures, but are better than not having them. And from that, you can compute the compute time and the memory time, and the latency of the Roofline model is the maximum between them. Again, it's not a perfect model, but we'll try to see whether it works better than using another imperfect model like the flops. So this is just an illustration of how different this could be on some, I think, state-of-the-art GPUs, basically. Maybe the more advanced one. And you can see that the ratio between the peak compute and the memory bandwidth between the P100 GPU and the V100 GPU is drastically different. And if you look at specific layers, again, this is Inception V2, you can see that the V100 is a faster GPU. So obviously, all the ratio between the latency of V100 and P100 is always smaller than 1. But relatively, some layers will be much faster, like 7% of the inference time, like the first convolution of first convolution, and later parts of the network are only 60% of the original, of the cost. The V100 will be 60% of the latency of the P100. So it kind of hints that there is a difference of whether you want to regularize towards P100 serving or V100 serving time. So we repeated the same type of experiments from a few slides ago, where we have Inception V2. We also added ResNet 152 to have like more diversity here, with the V100 regularization cost, latency regularization cost. So what you can see in the ResNet example, you see bigger differences between depth multiplier, the uniform shrinkage, and the MorphNet latency, V100 latency regularizers, and also in the P1 and the Inception V2, you see some gains as well. Again, if you remember, if you look at the y-axis to see the absolute gains, they are not necessarily super impressive, but they are consistent. But I would like to urge you to pay more attention on the x-axis and see that there is like significant, I didn't compute it here, but it's usually 20, 30% speed ups kind of for free compared if you fix accuracy and you are looking at speed ups. So that was very nice to see. Later, we actually did, of course, the same experiments with the P100. So clearly, we were somewhat disturbed specifically from the Inception V2 results that kind of look basically overlapping and not very impressive. And also the ResNet 152, there are almost no gains. And that was kind of disappointing. We tried to debug it for a long while. Lots of gray hair came from that. But eventually we were trying to hypothesize, like, why does that really happen? And if you remember a little bit from the numbers before, or maybe you know that V100 is a much faster GPU. So it's actually less compute bound. Almost never it's compute bound. Whereas P100 is often compute bound in these type of networks. And to validate this hypothesis, we applied the following procedure. We took Inception V2 and we created something we call subnetworks of, which we think is like randomizing the number of filters in each layer according to some procedure, and creating kind of trying to understand the space of what type of architectures are there to explore. And what you can see is that if you, for each of these architectures, we computed the latency for the P100 and V100 and the flop cost of it. And what we see is that for the P100, actually, there is a very narrow band that shows the correlation between the flops and the latency. And this is why when we regularize for the flop regularizer and regularize with the P100 latency regularizers, we basically get almost the same behavior because the networks, the cost is correlated. And of course, during training, you don't care about the absolute number of the cost, you only care about kind of the correlation and the direction that these gradients point you to. Whereas the V100, there's a lot more variety, a lot of more discrepancy between the flops and the V100 latency. Therefore, kind of having the right type of regularizer can benefit you. So that was reassuring that the results are disappointing, but there is a good reason that we can understand to some degree. So that was about the results and about the math and the algorithm. I'd like to try to convince you to use our, or at least to explore our open source framework that you can reconstruct all these experiments and do more on your data again and with your task. So it's actually pretty simple to use. So this is like a short example. What you need to do is clearly include our library. Then you build here, use the abstraction that we think of as a network regularizer. An instance of a network regularizer is the flop regularizer that obviously regularizes flops. And you see that you need to compute the regularization term, multiply it by regularization strength, pretty straightforward, and add it to your optimizer as a target. And notice there are two hyperparameters floating around there, the regularization strength and the gamma threshold, and I'll tell you a little bit about how to think about them. So first of all, the regularization strength. It seems like this magical number that comes from somewhere, but actually it's relatively easy to tune. We usually start with 1 over the cost of the network, whatever the relevant cost is, as a ballpark number. But then when you sweep over a handful of regularization strengths, you see a very consistent behavior of the stronger the regularization, the smaller the network. Not very surprising. So it's actually pretty easy to tune to find a number that will reduce the flops or the latency by a desirable amount. You can also easily see that when the regularization strength is too weak, nothing happens. When it's too strong, way too strong, you'll simply kill the entire network. It will zero out. So it's not very hard to find the interesting regime. Of course, this is a trade-off. When you shrink the network, you might see some drops in performance. And again, the trend usually is very monotone. So when you have regularization that is very weak, sometimes it actually can help performance a little bit, but basically it will have no change usually. And if it's stronger, you might lose something in performance. There is a threshold. So I didn't mention that explicitly, but when you apply, in the classical world, you'd apply, you wouldn't do L1 regularization with stochastic gradient descent. You'll apply other methods, which we do not usually apply at deep networks. So you don't necessarily reach an absolute zero. So you get to small numbers. So what we can do, what we usually do is we plot the element that we're regularizing. It would be the gamma or the L2 norm of the layer in a histogram. And we usually see this bimodal behavior where there are, okay, there's some delay here. Okay, sorry about that. I don't know why slides don't advance. Can someone help me with that? I think it's stuck. Yes, totally frozen. Escape? Remind me of the Microsoft days. Sorry if there are people from Microsoft here. I didn't plug it. Here.
Switch it to the DP. Okay, go back. Okay, go ahead, plug it in.
I want extra 2 minutes.
No, go ahead.
Okay, yay. Okay, so we have a live filters with that have some amount of. I think I'm good.
Just to make sure.
Yes, so we have some number of filters that we know that are alive. They have some reasonable values, and there are others that are. You can see that they are kind of the network wants to kill them. They are dead. We think of them as dead, and actually the threshold can be anywhere in between. It doesn't really matter. The network, the performance is not that sensitive. It's actually not sensitive to the threshold if you pick any threshold in between. Another element that you'd like to do is like if you're learning the structure of your network, you should be able to use it. That sounds very necessary. So we have this small tool, we call it a structure exporter, and it will save, while training you can do that, the current estimate best structure of the network. You can take one of these structures or the final one, and initialize the network for that. You need to add some trivial changes to your code and use this parameterization that you read from disk. So what I didn't mention is what do you really do when you reinitialize a network. So there are basically two options. So the problem is that because things do not go directly to zero, so if you zero them out, there is some jitter and the performance might drop and change, and this starts to open a can of worms that you don't necessarily want to open. Also, the regularization itself might kind of hurt performance because the networks are actually very picky and you add this type of weird regularization. So the performance from the first stage does not necessarily represent everything you can extract from the network. So this is why we need a second stage. And now, tell me it's not stuck again. So now you have like two basic options. One of them is to try to zero the things that are close to zero manually or somehow and fine tune, or you can train from scratch. We actually prefer the training from scratch for two different reasons. First of all, it assures that the structure that you get eventually is basically standalone. You can forget where it came from. It's kind of magic numbers that you only use once, and you can continue training it for a while till your data changes enough, or your metrics change enough, or whatever something happens, and you can revisit the architecture learning. You're not married to this process of every time you change something, you have to retrain from scratch the architecture as well. And it makes everything slightly more reproducible. Furthermore, it also will stabilize things down the pipeline. Your optimization and whatnot can be tuned to this specific learn structure. I don't have really a lot of time to tell you about things under the hood, but under the hood, some interesting engineering is happening to take into account all kinds of things that happen within networks. Residual connections, you'd definitely want to ensure that the structure that you're learning is compatible. It will be very awkward if the first convolution has 17 outputs and the second convolution 35. You'll try to add them, not a pretty story. So we have to take that into account. It gets more complicated with concats and all type of other operations. I won't get into that. You can take a look at our code and some documentation, or contact us if you're interested. And because I'm in a negative amount of time, I'll jump to, first of all, thank all the people that were working on that, specifically our team that consists of Max, Yair, and Andrew, sitting here, and quite a few other collaborators in Google across the time of the existence of this project. Thank you very much, and I urge you to contact us at morphnet@google.com or check out our open source at GitHub. Thank you.